So I went around my school asking my friends about their SAT scores and their average family income. After some tedious work, what I have now is my data distilled into some discrete points on the graph. Now I wonder two things here. The first one being, how do I join these points with a continuous function? Well, after some algebraic manipulation, I went ahead and found a polynomial that joins the points as shown. Then, however, my other friend, let's imagine I have some for the sake of the video, did join the curve like this. And that got me thinking, which one is the correct one here? Well, I for sure know that mine is less wobbly, so I'd pick mine. However, the real answer here is we simply can't tell based on the given constraints. We need more information. Now, this video is not about curve fitting and interpolation. So the second important thought that came to my mind was, which curve would be a better curve for my aim of determining whether increasing income increases SAT scores on average? To answer this question, I had to discover regression the way it was meant to be discovered. Let's go back to my graph. I'll be using my polynomial here to connect and join all of these points. Now, going back to the question if increasing income increases SAT scores, we see that there are some intervals as marked by green in which SAT score seems to increase with increase in family income. And in some interval, as highlighted by red, family income seems to decrease with increasing SAT scores. So maybe that's the answer here, right? Maybe the answer here is it increases for some interval and decreases for some interval. But I have two problems with that. Number one, as mentioned, this curve really isn't accurate to model the data. I mean, you don't have any definite evidence under the current constraints that this curve is the correct one and models the discrete data well. Number two, the conclusion seems moot here. I mean, increasing for some interval and decreasing for some interval, that isn't justified at all. Like, why would the data not follow a general trend overall? To address these problems, if and only if I had some linear function like this one that could model the data well, then I could easily check for the general trend by looking at the slope. If the slope is positive, I could conclude that an increase in one variable leads to increase in another. If the slope is negative, I could conclude that decrease in one leads to increase in another. I mean, a linear function would be really viable, would be really useful here. And that is the core essence of linear regression. Finding a linear function that could model the data well and give us the general estimation of the trend of increase or decrease of data with each other. It is literally the process of finding a linear function that could model the data in some sense that we'll be discussing about later. Now our main objective should be first to determine the sense via which we could conclude that a linear function models the data well. For that purpose, let us take a blind eye here and picture a linear function. Well, this one would be the one I go with, but here's the question, what sets this line apart from this one? In other words, how do we measure the quality to which the data is modeled by the linear function? Well, I mean, if we're diving on first intuitions, our guess here might be to consider the vertical, or of course equally likely horizontal distances from the points to the line. I mean, that's a good guess because, well, you're in some sense measuring how much the data deviates from your proposed line. So maybe we say our line is good or bad based upon the sum of all of these distances, which we'll call the residual distances. Optimally, we want the residual distances sum to go to 0. I mean, this is viable, or so it seems. Or does it? Well, jokes aside, if we're moving on with our first intuition of judging a line based on the sum of residual distances, we arrive at a problem. Say, for these set of points, if this was a line we're trying to judge, the sum of all the residual distances here is 0. The residual distance below the line is equal to the residual distances above it. And of course, for the sake of convention, we have to consider one side of the line as having a positive residue and the other one having a negative one, because if we don't do that, we won't know if the line overshoots or underfits the approximation for the data points. So as of now, for this line, the sum of residual distances is, well, 0. And now, for the other case, the residual distance here is 0 as well, simply because there's no residual distance here. So do you see the problem here? Do you see the bigger thing we're trying to tackle? If we're considering the sum of residual distances as a viable parameter to judge the line, we would treat both of these lines as equally viable to model the data, which of course isn't, because the second one does a far better job at it than the first one. So at this stage, maybe we need not to consider the residual distances sum here. Maybe we want to consider something that tackles this problem, something along the lines of the sum of residual distances, but squared. So while building on the idea of the sum of residual distances square here, let us go towards a more mathematical approach now. Labeling all of the points in our dataset as x1, x2 and so on, and their respective y-coordinate as y1, y2 and so on, denoting them as x_k and y_k altogether. Now, let us also assume that the best fit line that models this dataset is given by the equation y equals to ax plus b, where of course a and b are constants. So now we're considering the sum of residual distances square here. Now, for the sake of the video, I'll only be considering the vertical residues, but of course this works with the horizontal ones as well, as I mentioned in the previous part of the video. So let us redefine the meaning of residual distances from a more mathematical manner in our system. It is just the difference of the y value of the line at a point in the dataset and the y value of the dataset at the same point. It could be the other way around, the difference could be the other way around, but since we're squaring it, it doesn't make a difference. No rocket science there. Then, the y-coordinate of the line at a point in the dataset, denoted by x_k, is of course given via the equation of the line as ax_k plus b. You get the gist. So, our new formula for residual distances is worked out as so. I mean, it is messy, but at least before anything, I could work out residues from a more mathematical perspective now. Well, before getting too ahead of ourselves, I had let out a very subtle discrepancy there. We know that we've denoted the best fit line by the equation y equals to ax plus b. But recall that since from the very beginning, what we're trying to do is find a linear function, this particular linear function that models the data well, we want the values of a and b to be highly optimal. But before this, let us step back for a moment and visualize what a and b really means in our system. A is the slope of the line, which basically controls the degree of tiltness here. As you can see, if we vary a, the sum of residues square also varies. In some case, it might increase from our original line, and in some case, s might decrease as shown. B is referred to as the y-intercept of the line, which basically shifts the line on the vertical axis, up and down. And the same goes for B too. Varying B in some case causes increase in S, and in some case it might decrease it. So let us recall our main objective here. Our main objective here is to find the optimal values of A and B so that the sum of residual distance squared is minimized. If you have just understood what I said, you totally get the core essence of regression now. But if you don't, I highly recommend going back to the video and watching this particular segment again, because this is the core essence and this is how we'll derive all the mathematical foundations later. So in short, we have to minimize this sum with respect to A and B. Now I think it's a good time to put out the fact that we have to notice that x and y aren't our variables here. The variables are A and B. As a matter of fact, x and y are just the fixed points in the dataset, and a and b are what we're seeking to optimize. So expanding this sum using the square formula, we're finally left with this hefty looking sum. But now let's move on to the main optimization part. We know that for some values of a, the sum s increases, and for some value, well, it decreases, as shown previously. Sometimes we overshoot a and sometimes we undershoot it, then the optimal value. But still, whether we undershoot it or whether we overshoot a, the value of s remains higher than the value of s at the optimal point. Visualize it like thinking about a upward facing parabola, where you're trying to find the minimal value by guessing the vertex point. Sometimes you go left of the vertex point, sometimes you go right of the vertex point, but at the end you end up with the functional value greater than that at the vertex point. What I mean to say here is only one value of a minimizes the sum s, but any other value of a ultimately goes on to increase s. So we have to optimize, we have to find the actual value of a that minimizes the sum. It's kind of like finding the vertex. So using basic idea of differentiation, let us take the derivative of s with respect to a. A more essential point to notice would be that this is sort of a partial derivative because we're dealing with two variables here, a and b. But at the end, if we're differentiating with respect to a, we just consider b as a constant and vice versa. So now, for the absolute minima or the vertex of the second degree equation of s with respect to a, we have to set the derivative equal to 0, and then we're left with this. Now the same process goes for b too, taking the partial derivative with respect to b and setting that to 0 for the absolute minima. Because the equation is quadratic with respect to b, we obtain another equation for b where b is optimized, which is this. Hence we're left with two equations after optimizing everything. And these two equations provide optimal value of s with respect to a and b. Now these equations are what is directly handed down to you in your linear algebra courses. But at the end, we just learned how to derive it with bit of calculus and the entire intuition of minimizing the sum of square of residual distances. In my opinion, this approach of learning is definitely more fun. Now, let's take a step back and analyze our equations. The sum from 1 to n of y, which means the sum of all the y values in our dataset, is constant for a particular dataset. The same goes for n too. N just means the number of data in our dataset. And the same goes for all the values of x summed in the dataset too. It is a constant. And if we're analyzing the second equation, we could go further. We could also see that the sum of the product of x and y values for a particular dataset is also a constant. And so is the sum of all the x terms squared for our dataset. What I mean to say here is that for a particular dataset, all of the terms are constant apart from a and b. So don't let the complexity of this equation fool you. At the end, it's just a linear equation in terms of a and b for a fixed data set. So I guess we all do know how to solve linear equations, right? So multiplying first equation by the sum of all the x terms and multiplying second by n and then subtracting them, the sum terms cancel out, and ultimately what you obtained is a nice little neat formula for a. And plugging it back into one of the equations, we obtain a closed formula for b as well. But do note that these closed formula are actually difficult to remember than the actual equations. So knowing the equations will suffice for now. But the main point is we now have a definite value for a and b, which are very optimal, which optimize the value of s. And now all that's left to do is put the puzzle together. So finally, a sigh of relief, plugging all of the values of summation terms and finally obtaining a values for a and b, we plot the best fit line as shown, where of course the main intuition behind our entire idea, the sum of residual distances square, is minimized. Now back to our objective, since the slope of our line is positive, we can say that the SAT scores correlate positively with family income, which does mean that as family income increases, SAT score increases on average too, for our dummy dataset of course. Now the intensity of the increment can be found out by using Spearman's or Pearson's correlation coefficient, but that's a topic for another day. Now I leave behind a question here. There is a special point that this best fit line, or in fact any best fit line, always passes through. Pause and try and ponder what the point is. It's the mean of x values and the mean of y values in our dataset. Can you figure out why this best fit line, or in fact any best fit line, always passes through this special point? Hint, it's based on the first equation we derived by minimizing a.